started. How's everybody today? First of all, just to remind, everybody knows this, the quiz Monday, the last quiz, 6, cover gravitation, universal gravitation, and it will cover oscillations. I have recorded the solutions for the video recording of the solutions for practice quiz 6. They're posted on the D2L website, so once you do that sometime over the holidays, I guess, you can take a look at that. Later today, I will record doing a bunch of extra practice problems. Okay. The suggested practice problems for quiz 6 are on this list here. This is available when you go to the practice problems folder. You'll see this set of problems, gravitation problems. By the way, I was looking at the gravitation problems and I was trying to figure out if it really covered everything I wanted to cover, and I realized it was missing some stuff, so I added 2 more just today. I added 2 more questions to the gravitation practice problems that use conservation of energy, and they have solutions as well for that. But anyways, gravitation practice problems, oscillations practice problems, then a bunch of problems scattered about from the various practice tests and such. Okay. Are there any questions about this? So I will select a few of these and make a video recording of the solutions that will be posted later today. The plan for today is to do a review of topics. I don't think it will take us to the end of class, so then we'll do a couple problems. We may end up a little bit early. So tomorrow there is no lecture in class. You don't have to come. In fact, I won't be around class time, so there won't be office hours tomorrow either. But to make up for that, on Sunday I will have office hours. And we're driving to New York City area. We'll try to make it back in time for the office hours. So unless you get an emergency email from me that we got stuck somewhere between New York City and here, I get 4:30 p.m. to 6 p.m. And the only place a good place is the same place I did it last time. That would be at the Snyder Phillips, the area in front of the dining hall. It's a nice open area. And the main thing is it's accessible. This building is closed on the weekend. Right now, so that's why we have to do here. Okay? Any questions about that? A couple things I should mention. Homework, unfortunately, continues to keep going, even though we don't have class. Okay, so there is no homework on Thursday, at least. They knocked that out. But there is my understanding, there is a pre-class homework that will be due tomorrow, even though we don't have an assignment. Okay, Wednesday at the usual time. So if that's really annoying to you, just do that right after class and get rid of it. Okay. And then there is a Sunday, there is a weekly homework on oscillations. Any questions about this? Okay with that? All right. I will send out an email tonight after I've posted the video of the extra problems listing all this stuff so that you can have a list of all these things I just mentioned. Okay, so let's get to the review of topics for the quiz 6. All right. Okay, so this is not quiz 6 material, but this is part of what we've been doing with planets and satellites, so let me just make sure this is fresh in your memory. So uniform circular motion we have centripetal acceleration. Okay, that's acceleration needed to go with uniform circular motion with speed v around a circle of radius r. Okay, so the speed v is constant, but the direction changes. The circumference going around is 2 pi r. So if you want to calculate how long it takes, or the period to go around one circle, so the distance is 2 pi r divided by the speed. So distance divided by speed is the time. So that's how you can calculate the period. And then the frequency is 1 over the period. So the frequency is the number of cycles per second, whereas the period is the number of seconds per cycle. Okay. Now the acceleration, as I said, the centripetal acceleration points towards the center of the circle. It has a magnitude a is equal to v squared over r. And the main thing I want to get out of this is not just the stuff over here, but the centripetal force is F net is equal to ma, so the net force needed to go around in a circle is m times a, where a is the centripetal acceleration, and that's mv squared over r. And that's used to derive things like the speed of a satellite that's going around in a circle. Okay, that'll come a bit in just a bit. Any questions about this? That's the centripetal force, v squared over r. Okay, then we get to universal law of gravitation. So we have two masses, right? M1 and M2. Notice, hopefully the notation is clear. F is for force, G is the universal gravitation, G for gravitation, M1 and M2, M's are for the masses. R, when you see R without a subscript, just plain old R, that means the separation between the two masses. If you see some R, like RE, that's the radius of the Earth, Rn, radius of the Moon. So when you have a subscript, it's usually talking about the radius of some object. But when it's just plain old R, think of distance between objects. Okay. So then G, M1, M2, M1 times M2 divided by R squared. And capital G is 6.67 times 10 to the negative 11. And the units is Newton meter squared over kilogram squared. The direction of this force is attractive. The masses attract each other. They pull each other in along a line connecting the centers. Okay. By the way, the distance is measured from the center of one object to the center of the other object. And so the force is along this line connecting the two centers. And it's attractive, meaning this is pulled with this force, this is pulled with this force. They're opposite directions, but they both have the same magnitude. Okay? Doesn't matter if they have different masses. This F will be the same force, that's magnitude that's felt from this guy by this guy, and it's the same magnitude for the force felt by this guy. Okay. Any questions about this? Okay. Now, if we specialize to an object on the surface of a planet or surface of the Earth, then we use capital M for the planet. That's just a standard notation. Small m for the little mass. It's on top of it's on the surface of the planet. Let's say capital, I don't know why I changed it to capital R, but that's to remind me that's the radius of the planet. So the magnitude of the force will be capital G, capital M times small m divided by R squared. Okay. That's just using the formula up here. And now, if I want to know the gravitational acceleration on this planet, then remember the formula is small m times, right? So I want a formula like small m times small g. That's m times small g. So then I can look at this guy here without the small m. I have capital G, capital M over R squared, and that will be the value of the gravitational acceleration for this planet. Capital G, capital M over R squared, where R is the radius of the planet. Is everybody good on that? And you could calculate the gravitational acceleration at any radius just by using some other radius other than the radius of the planet. You can just use any R there. Okay. Questions? Now, so this sort of problem so whenever you do gravitation, there's always these types of problems like, okay, you have a new planet, it's twice as big, twice as heavy, twice as small, or something's different about this planet compared to Earth. So what you need to do is you need to write down the formula. The force for this planet would be G times M for this planet times small m divided by r for this planet squared. And you have to write down the formula for Earth. Okay? And then you just compare what it is for the new planet versus Earth. This is sort of a standard thing to do. Any questions about this? Yeah. You can keep in this form, yeah. But when they ask for what is the gravitational acceleration, then you have to remove the small m. Okay? Because what they're saying is the net force is equal to m times the gravitational acceleration. Other questions? Pretty good on that? Okay. Let's go on. So for the case of Earth, then small g is equal to capital G, capital M for the Earth. Radius of the Earth squared. So plug in the values, 6.67 times 10 to the negative 11, 5.98 times 10 to the 24th. If you need the mass of the Earth, that will be given to you. Divided by the radius of the Earth, that would also be given if needed, 6.38 times 10 to the 6 meters squared. Well, some of these are actually on the equation. And then you get 9.80 meters per second squared. Questions about this? Okay, next we have satellites going in an orbit. So this could be just a plain regular satellite, an artificial satellite, or it could be a planet, for example, going around a sun, or it could be a moon going around a planet. It doesn't matter. So the small one has mass small m, the big one has mass capital M. Then the force, for the centripetal force, needed to go around the circle with speed v with radius small r. That force is provided by the gravitational force. So we have the net force needed to go around the circle, that's mv squared over r, that's a small m, okay, because that's the mass that's actually going around. And then the force of gravity is capital G, capital M times small m over r squared. Right, then you set these two guys equal to each other, because this is gravity, this is the net force, there's only one force. We get v squared is equal to g capital M over small r. So then the speed for the orbit is square root of capital G, capital M over R. This formula is on your equation sheet. You just need to realize what it's talking about. Okay, this is for the orbit. The circumference of the circle, again, is 2 pi small r. So the period, the time to go around the circle is the circumference, 2 pi r divided by the speed. Okay, questions about this? Let's go on. All these notes are, of course, on the D2 website. I'll include it when I send out an email this evening as well. Now let's recall springs. So we've done springs before, but let's review some of this. Let me just make sure this is recording right, hopefully. Good. Yeah. Okay, so when we have a relaxed spring, there's some relaxed length. If it's hanging from the ceiling, there's some equilibrium length. If we extend the spring by some distance x, then we have a force Fx, and the component in the x direction is minus k times x. It's proportional to the amount you stretch it. And k is the spring constant. It has units of newtons over meters. If we have more than one spring that are sort of doing the same thing at the same time, like we had with that the mass with the two springs, you know, remember the demo we were doing last time, the spring on each end? It ends up having twice the spring constant as one. You have more than one spring, and they're doing the same thing. They're pulling in the same direction or pushing in the same direction. You just multiply by the number of springs that do the same. Okay, so now if you compress it, it also tries to bring it back to the center. So it just tries to bring things back to the center of the oscillation. Then we also had the potential energy for a spring. Spring potential energy, we have this relaxed length, we stretch or compress it by amount x. The potential energy, capital U, is 1/2 kx squared, where x is the amount you stretch or compress, and k, small k, is the spring constant. All right, then we have the principle of energy conservation. For an isolated system, the total mechanical energy, E mechanical, is K, the kinetic energy, plus U, the potential energy. And this is conserved. So the way you use it is K initial plus U initial is equal to K final plus U final. All right? And so we would use the potential energy either for the the spring or for let's say gravity, then we would need the formula for the potential energy for gravity, which is next. Okay, so universal gravitational potential energy. If we have two masses separated by distance r, small r, masses m1, m2, gravitational potential energy, capital U, is minus g m1 times m2 divided by r. There's not an r squared, it's an r for the gravitational potential energy. So now if one is the Earth, the other is some small mass, then if we are going to do that case, it would just be minus g me for Earth times the small mass divided by r. So r, remember, is the distance from Earth's center, and me is the mass of the Earth. Okay. Now, in some problems, they end up asking about altitude. Altitude is the distance from the surface of the Earth. RE is the radius of the Earth, and the distance from the center will be the radius of the Earth plus the altitude. Okay. So typically when they do rockets and satellites, they talk about altitude rather than distance from the center. Questions about this? All right, in order for a rocket to escape from the pull of Earth's gravity, the total mechanical energy needs to be positive. That's because when you're infinitely far away, your energy is always positive because the potential energy goes to zero, and you only have kinetic energy, which can only be zero or positive. So the minimum required speed is called the escape speed, and so typically you might see like an ESC for escape here. Minimum speed is called escape speed, and it's given by setting the mechanical energy to zero. So you actually do have this formula in your equation sheet. Just E mechanical equals to zero. How you derive it, you say 1/2 mv squared, that's kinetic energy, plus U, the potential energy on the surface of the Earth. We need this energy to be positive, or we need it to be equal to zero for the minimum speed. And then so we just solve this guy equals to zero. Notice that the small m's can be canceled out. Then we get v squared is equal to multiplying by 2. We get 2 capital G me over re. And then taking the square root gives you the square root of 2 G me over re. Okay. Any questions about this? I should mention the formulas for the orbit and the escape speed kind of look similar. Notice that there's a small difference here in that there's a factor 2 for the escape speed. That comes about because you have this 1/2 mv squared. When you derive this formula, there's no 1/2, it's just mv squared over r. Okay? It's a small difference. They're not the same formulas. But both are on your equation sheet. Any questions so far? Okay. I've met the amount of topics, the number of topics on this quiz 6, not that much. So I know it's a pain to have to learn this over Thanksgiving, but if you get it, you can do pretty well on this quiz if you get the topics, because there's fewer of them on this one. Okay, simple harmonic motion. This is with sines and cosines. So the prototype way of writing the position x of t is a, where a is the amplitude, times cosine times omega, cosine of omega times t. Omega is the angular frequency. It's the angular speed, but we call it angular frequency now because there's no circles involved. And so this phi is what's called the phase constant. Very often phase constant is 0, but if you really need to deal with the phase constant, it's there. It's called phi. For the velocity, it's just, this is on your equation sheet, these formulas. You take the derivative and you get minus omega times a times sine of omega t plus phi. If you take the acceleration, it's one more derivative. Taking the derivative of the velocity, you get minus omega squared times a times cosine of omega t plus phi. Okay. Any questions about this? All right, then if we're asked the question, what is the maximum value of the position? Maximum value of the position, well, the cosine is, the maximum value of cosine is equal to what? What is the maximum value? 1. Okay, so then maximum value of x is a. Minimum value of x is minus a, or the lowest value of x is minus a. If you're asked what is the maximum value of V, then, okay, minus times sign. So the maximum value that can have is 1. The sign can go from -1 to 1. So the maximum value that V can have will be omega times A. The maximum value that the acceleration can have is omega squared times A. Does everybody follow that? Is that pretty straightforward? Okay, that's what I've written here. Now the frequency is the number of cycles per second, so you have to divide omega by 2 pi. And the frequency has units of 1 over seconds, or what we call hertz. You can call it cycles per second as well. Any questions up to here? Oops. Okay, now the period is 1 over the frequency, so that can be written as 2 pi over omega. All right, you are responsible for being able to read these graphs, or in principle drawing these graphs, but obviously actually physically drawing them in multiple choice is not possible, but to be able to recognize this. Okay, so you have these bumps like this, right? This is your cosine. Okay. Then we have the maximum value you can have is the amplitude. The time from one point to the repeat, the first repeat of the point is called the period. So you can take any point. I can go from here to here. But make sure you don't go from here to there. If I went from here to there, that would be half a period. Does that make sense to everybody? You have to go to where everything looks exactly the same, going from here to there. Okay. Yeah, question? Phase constant, yeah. I'm not emphasizing it that much, but if you want to know what a phase constant is, that's how much is shifted backwards. Okay, so the amount it's shifted backwards will be equal to pi over omega. Okay. Anything else? Okay. So the mass on a spring, we already talked about this. We have the spring constant, okay? But for the mass on a spring, it oscillates about around equilibrium. And so there's an angular frequency omega. And the main formula here is it's the square root of k over n, where k is the spring constant and is the mass, of course. Okay, questions about this? So then if you have omega, you can get everything else. The frequency is omega over 2 pi. Okay. And so then it's 1 over 2 pi square root of k over m. And then the period is 1 over the frequency. And so then it's 2 pi, and you flip it around, m over k. Now, the prototype example is when you release the mass from rest. That's when the phase constant, oops, sorry, that's my computer going to sleep. That's when the phase constant equals to 0, so then we just have amplitude times cos A times cosine omega t, or x0 is the initial value at t equals to 0. Questions about this at all? Everybody good? All right. Then we have the simple pendulum. So the physical pendulum is not on the quiz. But the simple pendulum is the topic that can be covered. So we have a string of length L, a mass m. The string has a negligible mass. Okay, and so now we want to talk about the oscillations about away from vertical. And so we have an acceleration, small g, due to gravity. So it could be 9.8, but we could talk about a pendulum on different planets in principle. The formula is that the angular frequency is omega is equal to the square root of small g over L. So we could have a problem that combines simple harmonic motion with gravity. That would be kind of the problem with both topics. Because the g, small g, would change for different planets. Okay, so now then the regular frequency f is omega over 2 pi. So it's 1 over 2 pi square root of g over L. And then the period is 1 over f. The period is 1 over the frequency. That's 2 pi square root of L over g. Now, one last thing we can do is talk about the total energy, the energies. So let's do this for mass on a spring. We didn't really do this very much for the pendulum, so we do for the mass on a spring. So the kinetic energy, this is capital K. Since I have a small k for spring constant, I'm trying to be clear. This is capital K. It's 1/2 mv squared. If I have v, I wrote it before as v is equal to minus omega a sine omega t plus phi. If I put that in here and square it, and then use the fact that k over m is, so the use the fact that omega squared is k over m, then this m cancels out and I get 1/2 k a squared sine squared omega t plus phi. You don't have to remember this, I'm just showing you the derivation of the next step that's coming up. Then if I have spring potential energy, U, capital U, it's 1/2 k x squared. And then I have 1/2 k, x is just a cosine. So I have a squared cosine squared. The argument is omega t plus phi. Okay. Now if I add the mechanical energy up for both of these, the total mechanical energy, add this plus this, because sine squared is equal plus cosine, because sine squared plus cosine squared equals to 1, the sum of these two together, you get 1/2 k a squared, where a is the amplitude. And this is a constant. Now I've noticed this equation is actually quite useful, that the total mechanical energy, these days well, you can write it as total mechanical energy. Let's write total and mechanical both together. It's equal to 1/2 k a squared. It's not on your equation sheet, but that's a very useful formula. One way you can think about where this comes from is just simply when the mass is at its maximum extension, it's momentarily at rest. The velocity is 0. So there's no kinetic energy. There's only potential energy. And at that point, x is equal to the amplitude, a. So that's why when I add these together, I get 0 plus 1/2 a squared. So the total mechanical energy is just 1/2 k a squared. Any questions about this? Everybody good? Okay, so let's, since we have a little time, let's just do a couple quicker questions, then we'll call it quits. Okay. I'll do one easy one, then I'll give you one more challenging one. Okay, I have to load up the clicker thing. I guess I didn't get that going yet. Oh, maybe I did. Okay, all right, so a spring exerts a force of 10 newtons when stretched by 4 centimeters. The mass of 1 kilogram is attached to the spring. What is the period of oscillation? Let's give that a try. It's supposed to be rather straightforward.
Is this a hanging spring?
Oh, so it actually doesn't matter. It just, when you exert a force of 10 newtons, it exerts a force of 10 newtons when stretched 4 centimeters
Okay.
from equilibrium. Yeah. Yeah, vertical springs and horizontal springs really behave the same way. Okay, anybody need more time? Anybody's had a choice? I'll give you another 30 seconds. Okay, so people need more time? Good. Okay. If you haven't made a choice, then go ahead and make your choice. I'm going to close it up. Okay, let's see what people said. All right, people say B. Let's take a look. All right. So we have force from the spring. That's the x component of the force. And so the magnitude of the force, right, 10 newtons. So K, spring constant, times 4 centimeters, 0.04, so you have to convert that to meters. And we got that K is 250 newtons per meter. Then the omega, the angular frequency, is the square root of K over m. That's the square root of 250 over 1. And that's 15.8 radians per second. Okay. Now then we have the period is 2 pi over omega. That's equal to 0.4 seconds. Questions about that? All right, I'm going to give you a more challenging one to convince you to look at a challenging problem. So I'm actually going to take one. Let's see, I'll put it on this. So the problem is, let's just do it like this. Let me try to think. Should I make this a clicker or should we just do it together? Which one do you want to do? Clicker or do it together? Okay. All right, it's a hard one though. Okay. A mass is initially at rest. 20,000 kilometers from the center of Earth. question is, what is its speed when 10,000 kilometers from the center of Earth? Okay, so let me give you some data here that you may not have. First, the capital G is 6.67 times 10 to the minus 11 Newton meters squared over kilogram squared. The mass of the Earth is equal to 5.98 times 10 to the 24th kilograms. Okay? And the choices I'll give you are A, B, C, D, E. 6,300 meters per second, 7,400 meters per second, 8,700 meters per second, 9,600 meters per second, 1,800 meters per second. Okay? I'll open up the polling here. Let's see. Okay, this is more challenging. So one thing I like to have you think about when you do practice problems is what, if you were writing this problem for, yeah, and it's actually worth thinking about. Suppose you were the professor, the instructor for a class, you're writing a problem, you're trying to have your students learn a concept. You should ask the question, what concept is being learned here? What topic are we trying to cover? And so what are some of the things that this is coming? Just throw it out at me. Well, what's a concept this is testing you on? Conservation of energy. Yeah, does everybody see that? Conservation of energy. If that's not screaming out at you, read the problem more carefully. That's exactly what needs to be done. Conservation of energy. So maybe what other concepts? Maybe not more minor things. What else is this testing you on? Yeah, gravitational stuff, right? Like gravitational potential energy, this formula, kinetic energy, these things. The other thing, when you're doing a problem like this, you notice I didn't write the mass of the object. So the mass apparently, either I screwed up and I forgot to write it, but let's have faith in have faith in me, okay, that it doesn't matter. So you can just set the mass to 1 there. All right, we're running out of time. I told you I'd let you out early, so I'll try to keep my promise. So what I will do, I'll cut you a break. I'll leave the polling open, and I'll go over the solutions, okay? You can adjust your answers as we go through. All right, so this is actually number 9, one of the new problems I added to the gravitational list of practice problems. So you can take a look. Conservation of energy. K initial plus U initial is equal to K final plus U final. The initial kinetic energy is 0 because it starts from rest. Then we have minus G m small m R initial is equal to 1/2 mv final squared plus minus G capital M small m R final. Notice that m appears everywhere, so we can divide through it by m, so I can get rid of the m's, or you can just set it m equals to 1, it wouldn't matter. Okay, so I have minus G capital M over Ri is equal to 1/2 V final squared minus G capital M over R final. So this is R initial, this is R final. So we plug in G is 6.67 times 10 to the negative 11, put that in here, put that in there. Mass of the Earth is 5.98 times 10 to the 24, put that in here, put that in there. Then we have R initial is 20,000 kilometers. It's kilometers, so we need to multiply by 1,000. Then it's 10,000 kilometers over here. Then we get 1/2 V final squared, ends up being 1.99 times 10 to the 7th. V final squared is 3.99 times 10 to the 7th. And V final ends up being 6,020 meters per second. Okay, so the correct answer is A. You can click that in for credit if you want. Okay, so have a safe, fun, relaxing Thanksgiving, and I'll see you guys.
Yeah, that was, I just used my phone calculator, so that's why I got that, but it was still close enough to... Great. That's good.
I wanted to thank you for helping me yesterday.
Oh, sure.
I don't think I'll be able to make it today.
It's okay. It's okay. Just keep paying attention to what you can do without help by yourself with the equation sheet, and that is the measure of what you can do on the quiz. So you keep that in mind.
Would you mind if I emailed you some questions?
Oh no. You should do as much as possible.
Perfect. Okay. I didn't want to bother you while you were out.
Okay.
Holiday.
Yeah.
Okay, so
Hey, yeah.